Thank you, everybody. I am the Director of Research and Development for Computrols, and machine learning is a topic that we've been working on for a little bit now, doing research and getting results. And as a software engineer, I find it very exciting, but I have a feeling not all of you will. So we're going to try not to bore you guys to death too much today. And I'd really like to sort of take the approach where we're just going to get everybody familiar with what this stuff is, what it can do, and where you guys, what you might expect to see in the coming years. So we're going to break it down into 3 parts. I'm going to start off with an introduction to machine learning, just to give you an idea of what this new computer technique is. Then we're going to briefly run through how we see it being applied to HVAC controls. And then finally, the building automation system of the future. I'd really like to try and give you guys a vision of what this thing's going to look like when it's finished. To start off, machine learning is a branch of artificial intelligence, and it really has taken off in the last few years. And artificial intelligence, I personally don't love the term. I prefer machine intelligence, and everybody thinks of science fiction and Terminator movies and whatnot when you hear artificial intelligence. But machine learning is a real thing that has taken off in the last decade and is really producing great results in a lot of different areas. I'm going to start off just with some headlines, and I thought I would just give everybody an indication of what's sort of going on in the news. I know a lot of people wake up every day and read their news, and you might learn about the presidential campaign or what's going on in the world. I'm a nerd, and I wake up and I read nerd news. So today I woke up, and we've got 4 headlines that I Googled machine learning this morning, and these are from the past 24 hours, just to give you an idea of sort of how hot of a topic this is. So the first one's from Forbes, 10 Ways Machine Learning is Revolutionizing Manufacturing, was the title. Many of the algorithms being developed are iterative, designed to learn continually and seek optimized outcomes. These algorithms iterate in milliseconds, enabling manufacturers to seek optimized outcomes in minutes versus months. Another one is why Google's new machine learning center in Zurich headquarters is a killer stroke to wipe out its competitors. Intel readies chip to rival NVIDIA for machine learning. A lot of machine learning uses specialized GPU chips it's pretty processor intensive, and everybody's sort of striving for that market because they know that the number of machines that are doing machine learning are going to scale up. This last one was kind of fun. I read this morning. How a group of data scientists are saving the whales with machine learning. They kept trying to identify these whales that were going around the ocean, and there are 400 of them, and they're trying to track them, and they fly over with planes. And they said, well, Facebook can do facial recognition. Why can't we recognize these whales automatically? So the problem became far more similar to human facial recognition than we expected. They just took machine learning algorithms, trained up these things using photographs of whales, and now they can automatically identify the whales with computers. So some neat stuff. One of them, not from today, I think sort of sets the tone for the meeting here, is no industry can afford to ignore artificial intelligence. Every imaginable industry will need to reckon with this artificial intelligence sea change. This is from MIT Technology Review. And I think it sort of sets us up for getting ready for this in our industry. There are a lot of things happening, but I think people need to be aware of it before it starts happening. We need to sort of incorporate it into standards that are emerging and get everybody ready of how we're going to handle it, the types of things we're going to do. I want to start by giving a problem that is difficult for humans but easy for computers. It seems trivial, but it's just multiplication. Here we have 2 numbers, 27,000 whatever times 7,000, and it's 210 million. Computers do this really easily, and I'm sure all of us could do it if I gave you a piece of paper and a pencil. But if I asked you to do it several times, you'd ultimately make a mistake. So not only can computers do this, but my phone can do multiplication 4 billion times in 1 second, and it can do that 24 hours a day, all year long, and never make a mistake. So it's not just better, it's a lot better. Let's move on to a problem that is easy for humans but difficult for computers. We would ask Mouse is giving me trouble. I'm going to show you a picture, and I'm going to ask you to classify it as a car, person, tree, dog, or a building. It's 5 choices. We simplify it with multiple choice. And here comes the picture, and we all know it's a tree. It's not even difficult. You just look at it and you say tree. So this is a problem that turns out to be really hard for computers. To start, the tree itself is a collection of 1 million data points. If you zoom in on it, it's actually a bunch of little pixels. We've all heard pixels, right? And each one of them is represented by a number. And we feed this number to a computer, and we feed it 1 million numbers. It has no problem going through 1 million numbers, but it turns out to be really, really hard to take 1 million numbers and identify the object in the picture. For years, people have been trying to do this. So I would challenge anyone. I know you're not programmers, but if you were to sit down and pretend that you would script out some algorithm, okay, you're going to go to the first pixel, and we're going to look at it, and we're going to go to the next one, and a computer can just rip through any instructions you give it at unimaginable speed, but it still turns out no human can really sit down and script an algorithm to do this. So, you might say, well, just look for green stuff. If there's a lot of green stuff, it's a tree. Well, that might work in this case, but if you asked it to tell the difference between an oak tree or a maple tree, it would be impossible. Facial recognition, a lot of you guys have heard about this in the news, Facebook, everybody's doing facial recognition. It's another one where we take a picture, it's a bunch of pixels, everybody recognizes that face, I assume, turn it into numbers, and basically ask the computer, who is it? Humans do this really well, computers struggle with it. You could look for lines, you could try tracing lines, there's a lot of things you could do, but none of them have worked historically. To sort of drive this point home, this is a little bit fun. If any of you read the Wall Street Journal, this is a head cut. This is the picture whenever they're doing a piece on someone, and this, of course, is George Clooney. It's made up with pen with a bunch of little dots. And just to sort of get everybody familiar with how this works, if I asked you to write an algorithm to recognize faces, if you were to feed it a face like this, humans have no problem with it, but it has no color in it, so you're not going to cheat that way. Few shades of gray. It's not a black and white photograph. It's just a bunch of dots made with a pen. And there are very few lines. So the dots really suggest facial contours, and a brain makes quick work of this. So this is a picture of someone, and I've removed all the dots from his face. So if anybody can recognize this, I'll be pretty impressed. But so you add the dots, and you see it's Mark Wahlberg. So the only difference, going back, between that and that are a collection of dots in the center. And it's sort of amazing how quick we do this. No computer algorithm could go through that and say, that's Mark Wahlberg. So one final one that I like to show is character recognition. And the post office had been working on this for years. You send in an envelope. They use a camera, and they take pictures of the address, and they try and figure out what the address says. Again, turns out to be really hard. And I'm sure everybody's had this experience. You're sitting there surfing the internet, you're going to Ticketmaster to buy tickets or something, you see one of these things, right? Can everybody read that? BOMA 2016. It's called a CAPTCHA. And the reason they put those on there is to tell computers and humans apart. That's the entire point of it, is that they don't want bots to go around and buy a bunch of tickets automatically. They only want humans to use the website. And CAPTCHA stands for, I just realized I'm missing a C, completely automated public Turing test to tell computers and humans apart. It's a fancy way of saying we're going to try and trick you. So a computer would come along and try and figure out the letters in there, and the lines and the distortions in the letters would completely mess it up. And most computers can't do it. But these things are getting better and better. I've even noticed recently going to websites that they're making them harder, and I can't even do it. So I'll type it in, and I'm like, damn it, and it'll give me another one, and it'll keep doing it until I get it right. But the problem is that pretty soon they're not going to be able to do this, that the computers are going to be able to read all the CAPTCHAs, and they're not going to be able to tell the difference. Just summarizing, problems that are hard for computers: pattern recognition, recognizing patterns in large amounts of data, anomaly detection. How do you tell what's not normal? Humans are really good at it. You get used to something and then say, wait, something's wrong with it. And then prediction, looking at a bunch of data and trying to predict what's going to happen next. So us nerd people call it the curse of dimensionality. It turns out in math, for decades, we thought these problems would be easier. But it's not just that a picture has a million numbers in it. It's that each number represents its own dimension. And then if you try to train a computer to look at a bunch of images, it turns out there are hundreds of billions of possible relationships between each one of those dots that you have to search through and just pick out the most important ones. So it turns out to be a really difficult problem. And a neural network that does classification on images could easily have 10 billion relationships that they store and run images through. So it turns out to be a really hard problem. Machine learning is a solution to this, and pattern recognition is the one that basically gets all the glory in the news. You see image classification, speech recognition, right? You talk to your phone, it can now kind of understand what you're saying. Facial recognition. There are other categories as well: anomaly detection, network intrusions. They use machine learning for that. Credit card fraud. It turns out that's kind of hard, and what they do is they watch your credit card activity. I say they, the machine learning algorithm watches your credit card activity, and it notices when something stands out as, wait, that's not how this guy's normal buying pattern is. Medical diagnosis, prediction, weather forecasting is now using a lot of machine learning. Stock market prediction, retail traffic prediction, they predict how many people are going to come in on a particular day. These are all success stories with machine learning. So computers, what they have classically been good at, structured math, storing and retrieving data, rendering graphics, and then humans supplement that with recognize patterns, classify unstructured data, learn. Machine learning sort of ties all that together and does sort of all of the above, and it's going to turn out to be a great tool in many, many different instances. So let me go through the classic computer program that you would install on your phone or your computer is written by a human programmer, and he sits down, and like I challenged you guys to do when you looked at the image, could you write a program to do something? So he sits down, he thinks about the problem, he breaks it down in his head, and he writes very explicit instructions in computer language, compiles it, and then he turns that into a program and he gives it to users. Users get the program. Let's say you're doing your taxes. You get TurboTax, you feed it your own data, out comes your tax returns, and that's how programming has classically been done. The machine learning, it's a bit different. Programmers are still involved, but they set up what we call a mathematical model, and it's still just a computer program. It's a big computer program that, let's just simplify it and say it multiplies and adds a whole bunch of numbers together. What numbers? That's sort of the key. So the programmer sets up a math model, and then he goes into a training phase, and this is an example of what's called supervised learning. The programmer is supervising it. And so the first thing is you need a lot of data. You can't just show it 2 examples and expect it to build a model. So everybody's heard the term big data probably. So big data and machine learning go hand in hand. You need to feed it a lot of data for it to get good. So basically, it starts off where the math model just has random parameters in it. You feed it some data, and it guesses at the answer. In this training phase, you have both the question and the answer. You have it all. It guesses at the answer, and it's going to be wrong the first time, and it compares it to the real answer. And then it makes adjustments, and the math model gets a little bit better. You feed it more data, guesses again, and you just keep doing that over and over. And ultimately, the model gets trained up quite well, and that model makes its way into finished products that wind up in a user's hands, like Siri. The speech recognition in that product was built through machine learning. And in that case, typically the size of the data that they would use would be billions of words that have already been transcribed. So they play the sound through a machine, and then they already know the answers because they have it transcribed. And once it's finished, it can detect speech. So to give you an example, in our image classification, we would feed it a picture of you-know-who, and it guesses wrong. It says it's George Clooney. And then, no, it's Tom Hanks, and it goes back and it changes the model. And you just keep feeding it images over and over and over, and the model keeps getting better and better. And then ultimately, after some training period, you would come to a finished product and it would work. You would show it an image and it would know who it was. So that's the sort of the basic idea of supervised learning. You take big data, the programmer is involved, but he's more supervising it. What really programs the system is the data itself. The data actually molds it into what it is. And it's a little bit strange because even when it's finished, a person could say, well, now that I actually have a math model that works, let me look at it. Now I'll understand, you know, how to write code to do it. Well, you can't because it's a billion numbers. It's just a billion numbers that are sitting in this thing, and when multiplied together, it's right. It's still really hard for a person to actually determine what that is. This is a graphic I took from a programming open source website, and it helps programmers determine which type of model to use. And I'm not going to go through all this stuff in too much detail. I just kind of wanted to give you a feel for the different areas of that machine learning can help. But you go with start, and the first thing it says is, do you have greater than 50 samples? Do you have more than 50 pieces of data? If it's no, go get more data. This is not going to work if you don't have a lot of data. As we said, it's big data. So sometimes you would do label data. Sometimes you would do clustering, which is a way of looking at a bunch of data when you don't have the answers and you're just going to look for it. And then regression is the one that in HVAC control you'll see. That's the one we use the most. It's better for time series data when you have like weather forecasting and that type of thing. So those are sort of the big areas. And the final one is dimensionality reduction. Most of the time you just don't use machine learning straight out on raw data because it would be too hard. So they usually go through a little pre-processing stage where they take the amount of data and they reduce it. And the fancy name for it is dimensionality reduction. So typically, if you're doing pattern recognition, you're going to use a classification algorithm. If you're going to do anomaly detection, you're going to use clustering, which is unsupervised learning. Prediction, you're going to use regression, and that's the one that I'm going to focus on most today. And is it still too hard? Well, then you do dimensionality reduction. So those are the big areas. I'm not going to go too much into the algorithm type stuff. I'm going to skip through this a little bit. This is a diagram from a facial recognition software package. It does dimensionality reduction to give you an idea. You start with an image with 1 million pixels, and not using machine learning, just good old-fashioned programming. We find a face, we then extract features from that face, and we reduce it from a ton of numbers down to 50 to 100 numbers. And then we take those numbers and we run it through machine learning. And that makes it doable. If we tried to just feed it raw images, it would be too difficult. So that sort of finishes up the part one with getting you guys an idea of machine learning, and hopefully you understand the basic process. And now I'll move on to what we're doing in HVAC with it. I wanted to start by saying with this corny graphic that HVAC, building automation, is a small industry, and a lot of times we lag behind the real big R&D. So, military defense, consumer electronics, mobile electronics, those guys have huge R&D budgets. I read the other day that the iPhone, they have 800 people working on the camera. That's just mind-blowing. So those guys are doing a lot of good research. The good thing about it is that a lot of research on machine learning is published. It's available to guys like us. And there's also a lot of open source software that you can sort of reuse. But we want to take all that R&D that's being done in these bigger industries, and we want to leverage it and use it in HVAC controls. I remember we were developing our newest controller, had a TCP/IP internet protocol connection at the controller level, and this was late 90s, and BACnet standards were coming out, and I always felt like BACnet took so long, and we were all doing a lot of internet-based protocols that they couldn't shift gears quick enough to sort of incorporating the new technology. And I was hoping that, with the development of machine learning and these newer things, that we could get faster, that is, we being the building automation, HVAC controls industry, we could get faster at adopting technologies into our standards quicker, not be so far behind the curve. But in building automation, you know, we showed the example of image classification, and the big data was a bunch of pixels and a bunch of pictures. So what is big data in building automation? It's the points. It's all that data we collect from the sensors and the outputs and all the other things that are in a building. But it's not just the raw data itself, it's the histories from these data. This is where the data really gets rich. We've been collecting history on every single point in our building automation systems since we began doing it. There was a time where it would eat up a lot of hard drive space, but at least for the last decade, it's not a problem. We just continually save everything all the time. So you might have 20,000 points in a building. They don't change all that often. A lot of things will go on once a day, go off once a day, and it's not really hard to store. Analog values drift around. But we're going to start with 20,000 points a year of data. That's my sort of bare minimum. When I'm going to do machine learning, I like to see a year. I don't want to train up a model in the summertime and then come to find out it's useless in the winter. So if I get one full year, I feel like I'm getting a nice average of all the characteristics in the building to build the model from. And what is the primary goal? There's a lot of things you can do. I've seen cool stuff that people are doing all over the place. I read recently about a company that's doing occupancy prediction. They're using neural networks to do occupancy prediction. So they try to figure out how many people are going in and out of the building. They actually sell that data to building automation companies. But with us, my main focus is predicting, using a model to predict values. So we're going to take a point, a single point of data. Let's say it's a space temperature, the temperature in this room, and we're going to look at the history of its own value, and we're going to look at other points that are associated with it, and we're going to try really hard to learn how to predict what it's going to be in one time frame. What's the temperature in this room going to be 5 minutes from now? And that's sort of the sort of basic building block for all of our modeling and everything. Each point gets a predictor, and those predictions come together to make a full model. And it turns out that you have to have predictors for every single associated point, otherwise the model doesn't work well. And I won't go into too much why, but it has to do with the interdependence between them. So before I get into that, what can models do? I just want to make sure everybody understands that. One, it can predict equipment behavior. So we're going to take a piece of equipment, an air handler, and we're going to set up scenarios for it, and we're going to say, how would it behave if we did this? And we're hoping that the machine learning model will help us do that. Detect equipment anomalies. Like credit card fraud, we are going to use the model to try and understand when the equipment is acting funny. Now, if a piece of equipment just breaks, we're going to know about it. We don't need fancy machine learning to do that. What we're hoping to do is what a human would do. He'd look at a cooling tower and he'd say, you know, something's weird about this. This is not what I'm expecting to see today. So we're hoping machine learning is going to do that as well. Run equipment simulations. We have been running simulations for a long time in our software that have to do just with outputs, and I'll go over that in a minute. But trying to predict what the building's actually going to tell us in a simulation is quite hard, and we're hoping that's going to help there as well. And then finally, given a model of all the HVAC equipment in a building, we want to run simulations of lots of different scenarios, huge numbers of scenarios, and pick the best one. And that sort of is the holy grail, is complete building optimization. So in HVAC, our predictions are going to be things like chiller load prediction. How loaded will our chiller be today, which will help us decide which chiller to run. KW demand forecast, occupancy prediction. If we can we determine how many people we think are going to come in the building? And what we're going to leverage is weather forecasting, things like that. There are algorithms out there, stock market prediction, retail traffic prediction. These are open techniques that other people have been successful at that are very similar to what we're trying to do. But in building automation, there are special cases. It's not just, oh, go get the weather algorithm and use it. There are lots of special treatment that we have to consider. The first one is, unlike weather, building automation systems affect the building. We're not just passively sitting back and watching what happens in the building. We're actually controlling the building. We also mix a lot of data types. So in the case of the image classification, it's all pixels. It's a lot of data, but it's all the same thing. In building automation, it's very disjointed. There's binaries, there's multi-states, there's analog data. So it's a real hodgepodge of data. And so modeling in building automation requires special treatment. And we like to break it down at a point-by-point approach and actually use these little pieces of models, and we use different ones for every type of point. So it's important to understand that we need predictors on every point, but in building automation, not all the points require machine learning. So machine learning is complicated, but we get a lot of free stuff. For example, outside output points, we're going to use our own control algorithms to predict what they're going to do. So take an equipment start-stop. It's off right now. Well, what is it going to be in 30 minutes? Well, it's going to be on. How do I know that? Because I have a schedule. I'm going to turn it on. I don't need, some brilliant model or math or anything to determine what outputs are going to be. They're going to be what I tell them to be. Weather prediction. We actually run our own weather service, and we do that now before we, go mounting, weather stations on roofs and stuff. You type in a zip code. We pull in weather forecast into our building automation system to help, what's the high temperature going to be tomorrow, and it'll help us schedule equipment in our central plant. So that's a great prediction. They're actually using machine learning, but it's not my problem. That's the National Weather Service's problem. And some points can use historical value. We've had inability to model certain points, and we say, but this point pretty much does the same thing every day. So let's just take an average of what it does at 2 o'clock in the afternoon, and that's our prediction. Other points are just constant values, minimum CFM, maximum CFM, set points. It's easy to predict. We just use a constant value. So only sensor inputs require the complexity of machine learning. We're trying to model the building, not the control system. So let's look at a couple of examples. Here we just took a small collection of points that are related to a single equipment. We got the unit start-stop, the thing that actually drives it. Unit status, that's the feedback, typically taken off a current transducer or something. Space temp set point, what do we want the temperature to be? The actual space temperature, supply air. And you'll notice some are ins and some are outs. So we only need machine learning on the inputs. And we have history on all these points. We have a year of data on every one of these things. So not only do we have the present value, but we have predictors on every one of them. You'll see controls engine, that's the actual building automation system. That's what we use to predict the output. Regression, and I'll go over that in a minute, that's the sort of go-to type of algorithm for machine learning. That's used on 3 different ones. And at the bottom, outside air temperature, we're going to predict that just using a good old-fashioned weather forecast. And predictors are required on every point, and some use machine learning, and some are actually much simpler. Regression, this is an example of linear regression in one dimension. And basically, you plot a bunch of data points and you try to draw a straight line through it. We never do it in one dimension. That would be like saying, I'm just going to look at the past space temperature values, and I'm going to know what it's going to be. You need more information than that, so we do it in multiple dimensions. And sometimes it gets nonlinear. But regression is all about drawing a straight line from what you know to what you would like to know. So point by point, we try to predict one based on itself and a bunch of other ones. So here's an example of a space temperature. It is the independent variable in red, and we're trying to just predict what it's going to be in 5 minutes. And to do that, we use history of it, plus supply air temperature, probably outside, the set point, the unit status, and the unit. and we run this through machine learning algorithm. We take a whole year, and we just take maybe one day to predict 5 minutes. Then we slide it over 5 minutes, and then we predict the next 5 minutes. We slide it over, and we slide it over, and we keep doing that. Then we'll move over to the next point, supply air temperature. We'll run through that as well, trying to build a predictor using machine learning. When we're done, if we have successful predictors on every single point, we have a full model. Once we have a full model, we can run it into the future, hours, even days. It's limited only by the accuracy of those individual predictors. And it depends on the equipment, but even changing things like outside air temperature and, on hot days and cold days, we can predict equipment days in advance. This little diagram just kind of shows that the way it is now, and most people and sort of the state of the art, we're not doing machine learning in the building. One of the problems with the building is it would be great if we could just build a building, fill it full of equipment, and go in and play for 2 months. We'll just turn equipment on and off and collect data and see what happens. Unfortunately, that's just not possible. Buildings have to be run. They have to be run a certain way. And we do this offline. So we take all the data and the history and bring it out to a data center. And in the data center, we run batch jobs to try and build these models. If the models are successful, then we can break off little pieces and bring it back to the building and then use it to model the equipment there. One good thing about it is we get to test these models offline. So a general rule in machine learning, you have all this data. In our case, it's a year's worth of history. A rule of thumb is you use 80% of it to train the model, and you use another 20% of it to test the model to see whether or not it works. You say, well, how can you test the model if you're not in the building? We already have all the data from the building for a whole year. So let's just say that we took 8 months of data, and we try and predict what's going to happen in the next time slot, and we slide over and we keep improving the model. When we get to the end, we still have several months left, so we predict what's going to happen into those months, and then we move over and we see whether or not it actually happened. So piece by piece, we can verify models before we go load them back into the building and actually use them for prediction. It is possible, and in many, we haven't figured out all the different cases. There are some things that just behave so strangely, we can't make a model. So it's okay if you can't model certain pieces of data. What you don't want to do is load up a model that doesn't work. So only the models that work and are pre-verified ahead of time make it back into the building. Dimensionality reduction. I had mentioned earlier that these problems are considered to be high dimensional. So basically, what that means to us is, if I have 50,000 points, I'd love to say, I'm going to use all 50,000 points to determine what the space temperature in this room is going to be. That would be impossible. That's just way too intensive. So we do have to reduce the number of dependencies. For this room, it's going to be the unit, it's going to be outside air, maybe it's how many days the unit was off in here. Did it collect a lot of heat and absorb a lot of heat? We try to get it down to a reasonable number. We're hoping to have them like 25 points or less in most cases. In certain cases, we can get up to 100 without running into too much trouble. But it is a problem. And we make these little small models, and ultimately we combine them into large models and use those. Some other challenges we've had, lack of variation. This one turns out to be huge. In the cases I showed you, we take an image and we feed it a whole bunch of different images. If I took 20 pictures of my colleague over here and fed it in, they would be different. He would wear different clothes, or it'd be different lighting. There's a lot of variation. What machine learning tries to do, it doesn't just memorize the answer, because that's useless. It tries to make a general thing that can be used in different situations. The problem with building automation is we go in, we have to get the building running, so we put schedules, we put PID loops, we put logic, and it turns out we run the building the exact same way every day. So you look at it for one day, and then you look at it for the next day, does the same thing. You look at it again and again and again. It doesn't matter whether you have 2 years or 1 year, you're not learning anything. So This lack of variation turns out to be a big problem, and it's something that we've spent a lot of time working on. We call it variation injection. So what we're trying to do is not mess up the building, but get it to behave a little bit differently every day and give the machine learning algorithm something it can sink its teeth into. So we try to control vary control sequences. We set boundaries, for example, on set points. If I can take a supply air set point and say, well, it's okay if it's 54 degrees or 57 degrees, and I'll randomly modulate in between there, it'll really, really help build that model. Intervals for schedules. On our optimum start, we usually put an interval. It has to be on by at least this time, but it can be as early as another time. One example of this is, I don't know, some buildings require that you don't start all the air handlers at the same time. Big motors, you turn them on, there's an inrush current. Sometimes you might see a light dim if a motor goes on next door. You can't go into a building and just bang 100 air handlers at the same time. So we have a feature to do a delay start. Well, before doing this, we would just specify the sequence. We'd start 1, then we'd start 2, then we'd start 3. Now, to do variation, we randomly sequence those. We'll start them in a different way every day because it's really unimportant to the building. We're already made the decision and we're not going to start them at the same time. So that's a good opportunity to inject variation. Another one would be loading up a chiller. I don't know how many of you guys are engineers or get involved in that type of thing, but let's say you got a tenant comes in early in the morning and you have to start his air handler. Well, you got to start a chiller to make that air handler happy. And if you don't start more air handlers, you're going to freeze the chiller up. It's just you have to load the chiller. So you just, okay, I got to start a bunch of more units too early. We found that's a great opportunity to randomly choose other air handlers so that every day we're building history with different air handlers, and then the machine learning can start to really sink its teeth into it and get a better model. So there's a lot of opportunities like that, and we're trying to identify those. Strategic placement of electrical meters. The real big, the big sell for a lot of this stuff is energy savings. So we can predict a lot of things, but predicting kW consumption is the ultimate goal. So most buildings will have one big kW meter measuring the feed into the building. So imagine that you were trying to figure out how much energy each little thing you did in the building burned in kW. You didn't really know it. Sure, you could have somebody go around and write down numbers based off manufacturer specifications, but you'd really like to learn it. If you're just measuring the kW demand in the building in one place, you've got lights, HVAC, plug loads. You bang on one light, you're not even going to see the meter move. So you say, okay, I'll add more meters. Well, you're not going to add a meter on every single piece of equipment. You're not going to put a meter on that light. So what we try to do is go in, look at the electrical drawings, and we strategically place meters in a way that helps us rapidly learn and understand the kW demand from each one. So if you had 15 pieces of equipment on one circuit, say I'm going to drop a meter on that circuit, and then over time I'm going to watch as I turn these pieces of equipment that are serviced by that circuit on and off. I'll learn the individual contribution of each one in the kW demand. So strategic placement of meters has been something that we've been spending a lot of time on recently. We go in, we analyze a building's electrical system, and if you can afford to put 10 meters, we'll tell you the best place to put those to get the most bang for the buck. So again, re-summarizing what these models can do: predict equipment behavior, detect equipment anomalies, run equipment simulations, and find optimum control. This final piece, I know we're talking a lot about algorithms and everything. This final piece is really just to give you somewhat of a description of where we see this going in a couple of years. I'm going to back up a little bit, though, and just cover the evolution of CBAS from this, from building automation systems from this perspective. Most of you are not old enough to remember this, but there used to be building automation systems that were master-slave. There was one computer, a bunch of dumb sensors out there, and all of the automation was done from a single computer. And we moved on to direct digital control, and we distributed those smarts throughout the building. It made it a much more reliable. Unfortunately, it made management of all the smarts a lot tougher, because now the smarts are broken into little pieces, sent around, and there's often no centralized repository for all that stuff. We decided early on in the DDC days to use the exact same data structures and algorithms in all of our controls and our front-end server so that it was easy to move these things around from place to place. And it turns out now it really is nice because we can use them for simulations as well. We simulate individual controllers throughout the entire building in one computer. Currently, the sort of state-of-the-art is analytics, and there are a lot of companies, a lot of startups that have come out and sell analytics services, analytic products. Most of them are rule-based. They sort of take engineering best practices, and they have these rules. It does produce better performance. Often it's human consultants. Some people will say, oh, well, we take your data and then we run it through these fancy algorithms. But a lot of times it's really an engineer supervising it, and he's just got his best practices. And it turns out to be good in a lot of cases. If nothing else, it is an audit of your practices. A control system may be set up some way, and it may be as simple as somebody overwrote a set point and forgot to put it back. Did you catch it in the building? No, but when you sent it off to your analytics guy, he did catch it. A lot of them are set point adjustments. They'll come back with set point adjustment recommendations. But it can be labor intensive. It's usually done on large pieces, and it's not continually done. It's done in a clump. You get your recommendations. Some work, some don't. You back it up. There's some period that you go through that. But that's pretty much the state of the art with analytics. We see this moving to machine learning, where we do the modeling, simulation, and optimization that I told you about. It's continual improvement, and really it penetrates down to even the smallest pieces. And we find that a lot of the things that you would find a really good engineer would go through a building and find a problem. Often it's very complex. It's not, oh, well, you could just raise your set points or you could do something like that. It has to do with the interaction of several pieces of equipment together, do something very strange and very unique. It doesn't happen in other buildings. It just happens in this one building. And identifying those things are quite difficult. So what's wrong with the current analytics? Often experts provide valuable knowledge with limited scope. They don't go through the whole building. They have expert knowledge. They know how things typically work. Typically, I can get away with raising a set point in this scenario. But they don't actually calculate the scenario that they're recommending. Insufficient time and resources to solve unique problems. Like I said, sometimes there are really, really tricky problems that a smart guy looking over several weeks or months of data could eventually figure out. That's one problem. He's got to do that 100 times. It's not really feasible in some cases. And we feel that true optimization has to be integrated within the control system. It can't be something that is done separately. I mean, you can take data away from a building, run some analytics, and come back with really good recommendations. But you can't run a simulation without having all the programming rules and so on and so forth. A true simulation requires that the machine learning and the analytics are built right into the control system itself. Just checking the time. So how will machine learning improve on this scenario? Even generalized rules will be applied individually with unique adjustments. So an optimum start, right? You know you can start the air handler later if it's cooler in the space, but learning from the individual room over large blocks of time will make it that much better. Again, extremely complex situations involving hundreds or thousands of points can be produced with machine learning. That would be something that even a smart guy in some cases spending all the time he could not figure out. We feel that at some point the machine learning algorithms are going to surpass even the best engineer's ability, just by sheer volume of data. And so, moving forward, we really see system convergence where a lot of the different building systems converge together. The more data you have, the better it is. So if you're trying to predict kW peak demand in an afternoon, if you're just a standalone HVAC system and you don't know what the lighting guy's doing, you're going to have a hard time predicting what that peak demand is going to be. So to really do a great job with machine learning and do building, we see that you really have to integrate data from a lot of different subsystems. New LED lighting systems are getting pretty sophisticated. A lot of them now, they'll sell fixtures with occupancy sensors built right on it. They're dimmable so that you can dim if nobody's underneath it, and you can get brighter when somebody walks by. That's great information that other systems could use to determine occupancy. So we really see that these systems really need to start working together more closely. One of the things that we're advocating for is these predictions that I keep talking about, the ability to predict data into the future, should be shared and available. Let's say in a BACnet standard right now, you can get live data between systems. Wouldn't it be great if you could ask your other system what his value is going to be in 20 minutes? That could really help me do something. Right now, I can ask the National Weather Service what the weather is going to be in 20 minutes, and he'll tell me. If I know I'm going to start a piece of equipment in 20 minutes, why wouldn't I share that data with someone else? The fact that it's off right now doesn't help him as much as the fact that I'm going to turn it on in 20 minutes. That's data he could use. So we have built in live data into our system that contains predictions. And we store as much as we can predicted values into the future. And we think that sharing between systems those predicted values is really going to help. We also use the predicted values in logic. We have pretty straightforward logic that you can do in English language, and this is an example of using a prediction in a logic statement. If prediction of outside air temperature in 1 hour is greater than 85 degrees, and AHU23 is on, then close outside air damper. It's a silly example, it's meaningless, but you see that you could grab predicted values and you could use them in programming and sequencing your equipment. It turns out in many scenarios when you have dependencies, like you got a big air handler and you say, well, I have to open this intake damper before I start the unit, and there's this whole sequence of things that one has to happen before the other. We write these long logic statements that sort of encompass the whole thing, and it really breaks down when you get halfway through and something doesn't happen. Then you got to sort of rewind and undo all the things that you did leading up to it. Breaking these down into these little predicted things that say, well, if the air handler is going to go on in 5 minutes, I need to open up and get ready for that. It's so simple, it just sits there. If it doesn't happen, if something happens, he just closes. So we're really looking forward to using these predictions in logic statements. Real-time energy pricing. We talked about how complex it is to optimize building performance, and we always say we try to run a scenario that has the least amount of kW. The truth of the matter is we want a scenario that spends the least amount of money. So utilities, and I'm sure you guys deal with this all the time, they have a problem that if everybody demands kW at the same time, they have to increase their infrastructure. They have to build new plants or whatever. So they want to encourage people to burn energy in off-peak times and conserve energy in peak times. So the old-fashioned way of doing this is a peak demand. But the smart grid, the whole effort that's coming out now, we're moving towards real-time energy pricing. Some utilities are offering it now. I think more and more they're going to be changing over. So as part of this promise, they're going to, again, give predicted values of energy pricing. So you can contact over the internet your utility and say, what is the price per kW going to be tomorrow at 2 o'clock in the afternoon? You can get this data. Well, if you thought optimization was tough before, wait till you try and optimize your building when the price per kW is a moving target. In many cases, it turns out to be cheaper to pre-cool a bunch of space before the peak happens and then just sort of glide through it. And having a qualitative understanding of that, of, oh, well, I think if I cool earlier, it'll be better, is completely different than actually calculating the number quantitatively. And we're hoping these models are going to really help carry through that. It's going to be really difficult to navigate real-time energy pricing every day with all the sophistication in the equipment. So it's something that we need to think about and get ready for. I call this alarms on steroids. An alarm, if you guys typically know, okay, I've got a space temperature. If it goes above 76 or it goes below 68, I'm going to red flag and a beeping noise, and you're going to hit F1 to acknowledge it. Those are great, but they're very, very one-dimensional. So what we want to do is incorporate more sophisticated, we call them notifications. And so it's push technology. We push on the user, something strange is going on. And they're built from these machine learning models. Usually involve many points. And it really comes down to this. I've built a model that will predict what I think an equipment's going to do. Most of the time, the equipment is going to do what I predicted it to do. When it doesn't, maybe there's a problem. Often there is, or your model needs to be updated. So these new notifications that come out of the model are going to be great. You know, coolant tower number 3, it's acting funny. You might want to look at it. Simulator mode, I touched on this earlier. We've been doing simulator mode for years, but it's just output. It's a great tool to do a bunch of programming offline, not on the building, and then watch your logic statement run and see the points change. But right now, it's only outputs. The inputs is anybody's guess. So we hope that originally we're going to have simulator outputs and then modeled inputs, and we can actually run the building. In this mode, you can use any screen. You can go into a graphic and you can see what happened yesterday. You can see what's going to happen tomorrow. You can go out and mess with the outside air temperature and see how equipment would behave. And we really think simulations are going to be the most powerful tool that you can have. Time scroll. We're doing this now, actually. We take history and we'll say, all right, I'm going to go offline. I'm going to Okay, yeah, 10 minutes. I'm going to wrap up in just a second. I'm running a little bit long. I'm going to give everybody an opportunity to ask questions. But we can scroll the time back and forth in graphics, reports, anything, and allow you to see what happened. And we're going to also do that with the future values.